Hello, everyone. I'm Pyonghwa Lee, an infotainment software developer at Hyundai Motor Company. Today, I'm here to present a paper I have written on the topic of software-level dynamic fault injection and diagnostic techniques. The presentation order is as follows. First, I will briefly explain the research background and introduce the dynamic fault injector proposed in this paper. Next, I will discuss the types of faults that occur in real products and the methods to diagnose them. Furthermore, I will explain the process of using the dynamic fault injector to forcefully inject these faults into the system and automatically diagnose or evaluate whether any issues occur. At the same time, I'll also discuss the internal components and operational mechanisms of the dynamic fault injector. With the recent emergence of the software-defined vehicle concept, the internal software of vehicles is becoming increasingly complex and flexible. The age of developing a vehicle once and being done with it is long gone. Instead, it has transformed into a continuous improvement and development era, where the traditional rigid development processes and fixed schedules are being challenged by their limitations. The cost of verifying the stability of continuously evolving and changing software is expected to grow exponentially, making it challenging to handle manually. Moreover, building a testing environment with diverse and expensive vehicle hardware is practically infeasible, considering the cost and time constraints. Therefore, there is a pressing need for software-level automated tools that can inject faults into the system at various levels, diagnose them, and evaluate their impact. The software-level dynamic fault injector I'm introducing today is precisely such an automated tool to address these challenges. The software-level dynamic fault injection tool, which can operate without any hardware support, was designed and developed. The fault injector is an automated system that can inject faults according to test cases, targeting a working system or specific tasks. And it monitors the results to verify that the system or task function properly and overcomes the injected faults as expected by the user. The fault injector is structured and operated as shown in the diagram on the right. The first module, the fault manager, generates test cases and manages injected faults. The second module, the dynamic fault injector, dynamically injects faults into the system or task. The third module, the system monitors state changes before and after fault injection and any abnormal symptoms. And the fourth module is the result analyzer, which collects output from each component and generates a final report. Detailed information about each module will be explained in the following chapter. In the system, faults that may occur or be injected or broadly classified into the following categories. First, there are faults related to insufficient available resources. When essential resources such as CPU, RAM, storage, or network become scarce, it results in reduced system responsiveness screen freezing, or unintended behaviors, potentially creating bugs. Second, operation delays and order changes. If specific tasks experience significant delays or forced changes in their execution order, it can lead to unintended behaviors or even cause severe damage to the system. Third, incorrect memory references and corruption. When certain tasks reference the wrong memory address, or when the referenced memory becomes corrupted, it can trigger anything from task termination to system shutdown. Lastly, nested events. In systems where events can be nested, similar to recursive function calls, mishandling resources during nested event processing can lead to critical system bugs. Our proposed fault injector in this paper offers an easy-to-automated approach to inject such faults into the system and tasks. One significant advantage is that it requires no modifications or addition to the existing software in the system. Merely executing the fault injector at runtime injects all specific faults. However, after fault injection, it becomes crucial to automatically diagnose whether the faults have been correctly injected and whether the system responds as expected. In the fault injector, I offer the capability to automatically monitor and record resource uses in the system and task targets after fault injection. Additionally, it can monitor the states of specific tasks such as stopping, restarting, or terminating. Moreover, it can track specific function calls, processing time delays, and abnormal return values for further evaluation. From the next chapter onwards, I will introduce each component of the fault injector and its uses. The fault manager interprets the test case specification written by the user in a certain format and generates fault tasks in a format that's compatible with the dynamic fault injector. Along with the generation of necessary fault task information for the result analyzer. As shown in the picture, the test case specification is largely divided into command, job, and run parts. The command section details the exact command to insert the actual defect. In the job part, the specific information about the fault to be actually inserted is described. For example, describe the name of the target function or task, the function's parameters, and the number of iterations. Finally, in the run part, the information required to execute the previously described commands and jobs in combination is configured. In particular, in the run part, the test case can be executed by combining the contents described in the command part and the job part, which then allows the expected system or task status to be received. Based on this, the pass or fail of the test case is determined. The dynamic fault injector, the central feature of the fault injection tool proposed in this paper, directly controls the task being executed to inject faults. These faults can be broadly classified into system fault and task faults, and further categorized by target execution location, fault type, and probability of the occurrence. The variety of faults that can be introduced through this dynamic fault injector is extensive. Some examples include memory value change, some argument value change, task force termination, external command execution through task, repeated function call, environment variable change, task stop, specific system call, specific function call, and available resource limit or forced function return. We can evaluate the success or failure of the tests by checking key indicators such as whether the target task terminates, if the expected functions are called, if excessive CPU usage is avoided, and whether the values at specific memory addresses align with expectations. The image on the right side illustrates a log of the task in which the dynamic fault injector injects a memory corruption fault into a specific task and then reads the memory area again every write function called. The system monitor actively tracks state changes both before and after fault injection, looking for any abnormal symptoms. The monitored parameters include resource utilization, task status, memory values, file sizes, and existence, function call frequencies, and return times, among others. The system monitor observes those parameters, aiming to identify any significant variations. Upon identifying predefined changes, it promptly triggers predefined handling commands. It's worth nothing that these handling commands are quite versatile, covering spectrums of actions. They include resource measurement commands for the system, tasks, and functions, as well as additional functionalities like memory dumps, task control, and stress testing. Finally, the result analyzer contrasts the expected result as described in the test case specification with the state after fault injection to determine if the corresponding test case passes or fails. It aggregates output from each components to create a final report. In this final report, we include more than just the pass-fail results for each test case. Specific expected and actual values are detailed as well. Furthermore, the report showcases the overall resource usage, throughput, the testing period, and displays the executed test cases and commands as events. Please refer to the graph on the right, which illustrates the CPU, I/O, and memory usage over the entire testing duration. The green boxes at the top indicates specific event occurrences. It's important to highlight that without access to the actual contents and data of the report, this description serves as a generation representation of how the final report would be structured and presented. For more accurate description, the actual data and results would need to be incorporated. However, you might be wondering, how does the fault injection tool manage to inject monitor, analyze automatically. It leverages an open source software named Guider for injecting faults, monitoring systems, reporting results, visualizing data. Allow me to briefly introduce you to Guider. How do we analyze problems that are challenging to reproduce? Issues like sudden stuttering, screen freezing, system reset, audio chopping, slow app launching or switching, and more can be difficult to be analyzed using simple logs. Often, they require system-level information. Even fleeting issue that appears and disappears suddenly leaves no time to connect the terminal for analysis. Sometimes there might be underlying issues that are not even visible to the naked eye. So how can you analyze these problems in an easy, quick, and accurate manner with minimal effort? The answer lies with Guider. Guider is a comprehensive performance analyzer that can monitor, profile, trace, and visualize various performance factors. It can function as a system daemon, constantly monitoring the system's status and activities. If a predefined resource or event reaches a specific threshold, Guider automatically executes designated commands to handle the situation. As depicted in the accompanying figure, Guider's specific operation begins by loading the config file during initialization. It then registers resource thresholds for each defined events and the corresponding commands to manage them. After that, the target resource usage is periodically saved and checked, and if this resource usage aligns with the conditions of a specific event, that event is triggered. When an event occurs, Guider sequentially executes the commands registered in the event. In addition, a separate report file is created and saved, summarizing the stored system information, including resource usage. This automation enables immediate problem handling with predefined commands when a specific problem occurs, or initiate problem analysis with a generated report. Remarkably, these functions operating continuously utilize a minimum amount of resources, typically of about 1 to 5% per second, based on one CPU core, only one CPU core. It's an incredibly lightweight solution, ensuring efficient and responsive fault monitoring and management without overburdening the system. Elaborated a bit on this seems to be a big selling point of this tool. In the demo, the occurrence condition of each event is defined as the threshold value of each resource defined in advance through the config file. These events are primarily categorized into 3 units: system, task, and device. System type attributes correspond to system-wide resources. Task type attributes apply to all or specific tasks, while device type attributes pertain to specific storages or network devices. It's not just hardware devices like CPU, GPU, RAM, storage, and network that are considered resources. Logical resources such as block, system load, file descriptors, sockets, and storage files are included as well. Additionally, various types of logs, functions, and IPC messages can be also monitored. Turning to the bottom of the screen, you will notice that when an event occurs, the automatically generated report files adhere to a regular naming format. All files begin with the execution order and number of reports, and then add the resource, occurrence range, threshold value, and time information related to the event. By default, each report is just text file, but it can be compressed and generated according to the guider's execution options. This compression function is vital, as automatic background creation of report files might lead to excessive storage use. If you use the option of the maximum size of the directory where report files are stored, the daemon will aim to maintain this capacity by deleting the oldest file if a newly created report file exceeds the specific size. This feature is particularly critical for mass production in the embedded world, ensuring that automated reporting is both efficient and sustainable. Next, let's dive into the contents of the report file that is automatically generated when an event occurs. Depicted on the left side of the screen, the top of the report file provides crucial details such as execution options, versions, runtime, load, number of tasks, kernel command line, and more. This information serves as valuable insight into each system and execution options across various environments. Following this, the report delves into information about system resources. Details about RAM, storage, network, and others are clearly displayed. What's remarkable here is that the report not only shows the system resources at the time the report was generated, but also this at the time the daemon was first launched. This allows you to gauge approximate resource changes and effortlessly discern the resources available at the time of event creation. If the previous page gave you a snapshot of the resources at the time of the event, what follows is an in-depth analysis of the longer-term resource changes leading up to the event. For instance, the top summary table shows the system resource usage line by line for each segment, showcasing various resources such as CPU, memory, block, and swap, reclaim, fault, context switching, interrupt, number of tasks, network. Can you see the resource change? Next, the top CPU info table. Here, we pivot from system-wide metrics to more granular insights. Specifically, the table displays CPU usage of threads in intervals, breaking it down according to each process and option. It also displays the minimum, average, maximum, and total stats for each process CPU usage. This level of detail is invaluable for identifying patterns like consistent CPU usage or sudden spikes related to specific tasks. But the resource analysis doesn't stop at CPU. The process level tables also encompass other critical parameters, including VSS, RSS, delay, I/O, cgroup, and more. This multispective approach enhances your ability to diagnose and understand the complexities of various resource behaviors. When analyzing a report, these insights can illuminate issues from several angles, providing a more comprehensive view of system performance and the contributing factors to any defective anomalies. Finally, this part delivers the most accurate details. Here, you will find detailed event and resource information that occurred in each section, offering a closer look at specific segments. Based on the previously summarized information, this part provides critical reference material when you need to drill down into particulars. Especially noteworthy is the specification of information relating to processes, allowing a detailed inspection of how much each resource is used in which area. In conclusion, this study represents a significant stride towards addressing the reliability challenges of incredibly sophisticated infotainment system. I have designed and developed a software-level fault injection tool capable of dynamically injecting diverse faults into a system or task. Remarkably, this is achieved without requiring hardware support or source code modification. Using this technique, we have demonstrated our ability to identify critical issues within a vehicle's running infotainment system by directing injecting various types of faults and validating the results prior to mass production or development. To ensure efficiency, we diverse the resource-aware multiple fault scheduling method and a multiple fault scheduling method. These innovations reduce the time required for complex and diverse fault testing. A standout feature of the technique presented is immediate applicability to all Linux-based platforms, CCOS, Android, Ubuntu, CentOS, without dependencies on hardware, software modifications, or builds. Beyond the present achievements, the fault injection tool shows promising potential for discovering kernel cases overlooked in specifications. Anticipated feature benefits encompass automating fault injection test case generation and validation to cut cost, reducing the cost of testing difficult to reproduce problems, improving product robustness and performance to enhance product compatibilities, and early detection of structural software faults early to curtail development expenses. At present, the use of dynamic fault injection tests at the software level for vehicle infotainment platforms by other developers, including OEMs, remains uncharted territory. As the complexity and safety impact of infotainment systems grow, the adoption of such dynamic fault injection techniques should be seen not merely on option, but on imperative in our quest to elevate quality. Thank you.